goal of Monday's proof clinic was to think about the basic structure of an element argument. So how do we use an element, an arbitrarily chosen element in a set, to prove an assertion about either the subset containment or the equality of two sets. So, for example, this was the fifth proof, the one that none of your teams were assigned, and so I'm going to talk a little bit about this one independently. In this one, part of what we have to prove is an assertion about, part of what we have to prove is that there's an equality between f of the intersection of u and v and the intersection of the images of u and v, respectively, and that needs to hold for all sets u and v. So at some point, we're going to need to implement an element argument in this proof. The other feature of this particular proof is that we also have an unpacking to do because of the if and only if statement that's up here at the top, right? And part of the craft of taking apart a statement to prove it is to figure out sort of how it breaks down, how it breaks apart, how to break one sort of complex statement into a series of simpler statements that we can prove individually. So anytime the statement that we're meant to prove has the if and only if structure, if and only if superstructure, the very first thing that we should do is to split that biconditional into the two individual conditionals. So we need to prove two things, both the forward direction, which would say if f is a one-to-one function, then for all u and v, we have f of the intersection is the intersection of the f's. And so I've sort of skeletoned out that part of the argument over here on the left, where if we're going to prove that directly, we begin by assuming that f is a one-to-one function, and we're supposed to then conclude, we want to show that for all u and v, f of the intersection is the intersection of the f's. So that would be the forward direction. And then I've also skeletoned out the backwards direction over here, where that would read, if for all u and v we have f of the intersection is equal to the intersection of the f's, then f is a one-to-one function. So I've skeletoned that out over here, again, kind of setting myself up for a possible direct proof, right, where I assume the antecedent is true, and then I have to somehow deduce the consequent is true. So that was the first thing, is that sort of unpacking of the logical structure. And in those cases where the assertion that we need to prove is a statement about containment or equality of sets, so that would be the case over here, because what I'm trying to prove is that f of the intersection is the intersection of the f's. Then, in that case, the element argument comes in the unpacking of that set equality. And we talked a little bit about this on Monday as well. So the statement right here, f of u intersect v, is equal to f of u intersect f of v. If we split that apart, we find that it also has a biconditional in it as well. And this is where the element comes in. So for an arbitrary element x belongs to f of the intersection, because there's an equal sign here, it's if and only if x belongs to f of u intersect f of v. And again, I'm going to renege on using x here in this context. Let me use y instead, just so that we can preserve an intuition about what these sets are in a moment. And so because that set equality is really a biconditional about belonging, a biconditional about membership in those sets, that means that we should break that apart as well. So we would have then two things to prove in that statement. We would have to prove, on the one hand, the forward implication that if y belongs to f of the intersection, so we would say suppose y belongs to f of u intersect v, then in that case we would want to prove, however we prove that y also belongs to the intersection of the f's. So I'll try and get that in here as well. Thus, y belongs to f of u intersect f of v. And that would be the forward implication for that orange star, this biconditional written in red up here. But then we would also have to do the backward implication, where we would suppose that y belongs to the intersection of the images. Y belongs to f of u intersect f of v. And then we would need to, from there, deduce, thus, y belongs to f of u intersect v. So that's a lot of logical unwrapping, right? We've got the one layer that comes from the if and only if in the original statement, and then afterwards we also have a biconditional, an unwrapping of an if and only if that's implicit in the equality of the two sets highlighted in red up there. So where we start with what looks like one statement to prove, we end up with what looks more like three statements. I've got one statement over here that I may or may not need to break apart. I don't think I do. I think this is probably as much as we need to do. But then the statement over here on the left turns into two statements on its own because we have a set equality to establish. And so that was the first objective, is to, again, get us back into that mindset where we're actually analyzing, we're taking apart the logical assertions that we have to prove so that we can break them into more manageable chunks, right? And each of those chunks we then are going to have to find some way of proving by, and this is the second goal, making explicit reference back to the definitions of the terms that we're using. I won't prove all of these assertions, but I do want to take the time to focus on this one. Okay. So suppose that y belongs to f of u intersect f of v. We want to prove that therefore y belongs to f of the intersection. I'm just going to draw this over here, and so that's the step that I'm going to try to prove. So to do this, the first thing we want to do is use the definition of, well, I don't want to use a definition of the image of a set yet, because the first thing I want to notice is that y belongs to an intersection. And about what does it mean by definition of intersection for an element to belong to the intersection of two sets? Yeah, it has to belong to both of those sets in turn. So by definition, I'll just write by definition, y belongs to f of u and y belongs to f of v. Y belongs to f of v. Okay, so we know both of those things are true. Now is the time where we can take each one of those and refer back to the definition of f of u and f of v. These were the things that we had up on the screen yesterday. So the fact that, for example, y belongs to f of u, so if y belongs to f of, and I'm going to make this a here into a u, right? Well, f of u is defined as the set of y's such that there exists an x in our set u with y equal to f of x. So what's great about this is that it lets me take that conclusion, lets me take this thing right here, oops, there we go. It lets me take that assertion, there exists an x in u such that y is equal to f of x. And now I get that in my proof. I now have a statement that I know to be true by the definition of image. So if I go forward, I can use that definition to now say, thus, there exists an x in u such that f of x is equal to y. Right? And if I apply the same logic using y belonging to f of v, what do I get to conclude? There exists an x in v such that f of x is equal to y. All right, so there's a slight problem with what I have written here. That was a faithful application of the definition of image. This was a faithful application of the definition of image. So what's confusing about this right now? What do we not know for sure? Yeah, we don't know that these two x's are the same, right? Each of the definitions only asserts the existence of an x, but if I invoke that definition twice, I'm not guaranteed that those definitions are going to provide for me the same x, right? So we should find some way of telling those two x's apart. How should we do that? That sounds like a plan. Let's call the first one, the element of u, let's call it x1. So f of x1 is equal to y. And for the second element, let's call it x2. That's the one that belongs to v. So f of x2 is equal to y. Okay, great. So now we've produced, let me see if I can diagram this out here. We have a set u over here. We have a set v over here. In principle, we don't know what the Venn diagram for u and v looks like. But we have produced an element x1 in u and an element x2 in v. And by definition, we've seen that the image under f of each of these is both equal to y. Right? So here's kind of the picture that we have set up. Okay. So, okay, what do I know now? What am I trying to prove at the end of this? I'm trying to prove that y belongs to f of the intersection of u and v, right? All right, so how am I going to get there? I need to show that, according to the definition, let's go back to the definition one more time. Let's apply the definition to the intersection. In order to show that y belongs to f of the intersection, u intersect v, I need to show that there exists an x in where? U intersect v, such that y is equal to f of x. So in other words, I need to establish that y is the image of something that belongs to the intersection of u and v. How in the world am I going to do that? Right now, I only understand that y is the image of variously something that belongs to u and something that belongs to v. So how am I going to find something in the intersection of u and v that maps to y? What do you think? What haven't I used yet? I haven't used my assumption that f is a one-to-one function. Now remind me, what does it mean for a function to be one-to-one? Only one element maps to one element. In other words, two different elements cannot map to the same image for a one-to-one function, right? But look at the picture over here. x1 and x2 look like two different points mapping to the same image. So what do we get to conclude? Assuming that f is one-to-one, right, assuming that f is one-to-one, we get to conclude that x1 and x2 are in fact not different. In fact, they're the same element. Let's write that rigorously, and then we'll be done with that step. And we'll be done with what I want to prove right now. So looking at what's written here, f of x1 is equal to y, and f of x2 is equal to y. So in particular, f of x1 is equal to f of x2, because they're both equal to y, right? But because f is one-to-one, that implies, because f is 1 to 1, that implies that x1 is equal to x2. Because after all, that is the definition of one-to-one. Okay. So the picture that we drew here is not particularly accurate. In fact, it's kind of misleading, right? So let's clean it up, and then we'll find out what we actually did here. So we showed that, in fact, the x1 and the x2 that map to y can't be different. They have to be the same point. But what set does x1 and x2 belong to? How do we know it belongs to the intersection? Yeah, because x1 belonged to u, x2 belonged to v, but if they're both the same point, so if we call them both x, let's say, then that point x belongs to u intersect v. And therefore, by definition, y equals f of x, and x belong to the intersection. Therefore, by definition, y belongs to f of the intersection.